Okay, so we're setting up lesson 95. We began this short unit by talking about how observational studies cannot show causation. And one of the biggest reasons why they can't show causation is because of this idea of confounding. There may be some other variable that's affecting both of the things that you're looking at. So we can't be sure that there's not a confounding variable unless we do an experiment. And the thing about an experiment that helps us with confounding is the random assignment. So when we have the people that are participating in our experiment, our subjects, they need to be randomly assigned to the treatment groups. So we went through and talked about the basic ways to do that, and today we're talking about the more complicated ways to randomly assign. So I've mentioned once or twice that when you do an experiment, just like in sampling, you want the people participating in your experiment to look like the population you're interested in. So when we were sampling, when we were just watching people or asking questions, to ensure that our sample looked like the population, one of the best designs that we could use was a stratified design. So we can go through and determine how many from each group we want to take so that our sample really does look like the population. When it comes to experiments, that's called blocking. It's this same idea of trying to make sure that if there are different groups in my population, I want for the people in my experiment to look like the population and have those same groups. So when it's a sample, we refer to it as stratifying. When we're in experiments, it's called blocking. And we have to be really careful that we know stratifying and blocking are not the same. They're similar, but they're not the same thing. So a block, when we use a block design, a block is a group of experimental units that are known before the experiment to be similar in some way. So that first blank is the word similar. Sorry, I'm just looking for my key. They're similar in a way that's expected to affect the response to treatment. You want to block the variable that you think will have the strongest effect on the response variable. So, didn't last very long. Some of the most common things that you would use as a block: age, gender, weight. So those are the first three. If you are trying to test whether or not a blood pressure medication is effective, you would probably want to block the variable of weight, because I bet you people's blood pressure is affected by their weight. So you want to block the effects of weight so that you can really tell if it's the medicine that's affecting the blood pressure, or if the medicine is having any effect on the blood pressure. So when we say we're going to block a variable, we're literally trying to block the effects of that variable. So some other ones that are less common are experience. Even like a GPA could be a blocking variable. So we're going to look specifically at this using an example about a mobile phone company that is considering two different keyboard designs for their new smartphone. So they have two different designs. They've labeled them A and B. The company decides to perform an experiment to compare the two keyboards using a group of 10 volunteers. The response variable is typing speed measured in words per minute. So essentially what they're trying to figure out is which design allows our users to type the quickest. How should the company deal with the fact that 4 of the volunteers already use a smartphone, whereas the remaining 6 volunteers do not? So the idea here is we don't want all of the users to be in one of the groups, because the people that know how to use a cell phone are automatically going to type faster than the people that don't know how to use the cell phone. So if you put all of the people that know how to use the smartphone in group A, and group A types faster, you won't know if it's because this keyboard's better or if it's because you put all the people that knew how to use the phone in that group. So you have to make sure that you have the same amount in each design or in each treatment. So we're going to block based off of experience. Within each block, we will randomly assign each volunteer to a treatment group using 2-hat method. If this were the actual exam, you would then describe how you would do 2-hat method, or how you would carry out 2-hat method. Because we're just looking at an outline of what blocking is, we're not going to do that in this space down here. So here's what a block design looks like. We're just going to draw a picture of it. We have 10 volunteers. And we need to break those volunteers out into 2 groups. We have a group of 4 users, meaning these people know how to use the smartphone. And we have a group of 6 non-users. These are our blocks. So we are blocking by experience. We're literally trying to block the effect that someone knowing how to use the smartphone would have on the response variable. So within each block, and we should highlight that or circle it up here, after you block, within each block, we will randomly assign. So we're going to split these 4 users into the 2 treatments. One of those treatments is keyboard A. One of those treatments is keyboard B. We're going to do that by randomly assigning them, and our method will be 2-hat method. So I'm just writing RA coming out of those so that I remember that I'm going to randomly assign those. So if we have 4 users, how many will be in each treatment? 2. So group A will have 2, group B will have 2. Then we do the same thing for the non-users. We break those subjects into 2 groups by randomly assigning. Half of them will go to A, half of them will go to B. So this time you have 3 subjects in each group. Then, after they do the experiment with the keyboards, you want to compare the users against each other. So which keyboard allowed them to type faster? You'll compare the non-users with each other. By doing that, you eliminate's not the best word, but by doing that, you block the effect of their experience on the results. We can look at these two together, knowing that these people are going to type faster overall than these people. These people know how to use a smartphone, these people don't. So their scores, both groups, are going to be probably higher than these ones. So we compare theirs together, we compare theirs together. After we do that, we bring our results together, and you can compare these. So we combine them back together, we can compare them, and then we can make a conclusion. So if the keyboard type A was faster for both groups, then you can conclude that A is the better keyboard. You don't have to worry about, well, did A work better because a bunch of these people already knew how to use the cell phone or the smartphone. Is that making sense? Okay, down here, I'm just going to quickly draw my two-hat method on what that would look like, because I think as we approach the exam, we really can't see two-hat method too much. So, to assign these, the best way to do it is to use two-hat method. I like to just draw the hats because it's faster. The other reason that I draw the hats is because I feel really comfortable being able to write out the bullet points for hat method or two-hat method. And I know that when it comes time to take the test, I'm going to be just fine on that. So I don't write it out in my assignments unless I have to. So this hat will be the users. You'll have 4 names in this hat. This hat will be the treatments. You'll have 2 slips with A on them and 2 slips with B on them. You'll shake these hats. I don't know how to make it look like I'm shaking them. Take 1 out of each. So this is my visual reminder of what I need to do when it comes to two-hat method. In one hat, I'll have the subjects. In the other hat, the treatment. Shaky, shaky, shake. Take 1 out of each. Match them up. Do that until all of them are assigned. So this is the random assignment for the first block. If you wanted to draw out the random assignment for the second block, it looks almost exactly the same. It's just you label the hats slightly differently. If you're pinched for time on your actual AP exam, I would draw out a picture of what you're going to do instead of writing out what you're going to do. Because depending on how clear your picture is, you could earn full credit for your picture. So this time 1 hat is non-users. So this would be 6 names. 3 for keyboard A, 3 for keyboard B. Shaky, shaky, shake. 1 out of each. So we do that for each group, each block. So when we're talking about block design, we are literally trying to block the effects of a variable that we know will affect the response. So in this case, we know that whether or not these people knowing how to use a smartphone will have an effect on their typing speed with either keyboard. Okay, so the next page describes a very special block design. So all of the methods that we look at today are block designs. This is the basic block design. A more complex block design is called matched pairs. At the top, I'm just going to say or remind myself that this is a blocked design. Is a block design. He's just a special one or a very specific one. We're carrying on with this idea that we know there's a variable that will have an effect on our response. So, a common type of randomized block design for comparing two treatments is a matched pairs design. So we have to keep in mind here that this is for two treatments. The idea is to create blocks by matching pairs of similar experimental units. So we're literally talking about a pair, two people, two subjects, two things. Then we can use chance to assign our treatments. This says it determines who gets the first treatment. We should just say who gets which treatment. So we'll pair two experimental units together, and then we can randomly decide who gets which treatment. So we're going to pair two experimental units together and assign them to one of the two treatments. So assign each one to one of the two treatments. Matching pairs helps us account for the variation among experimental units. And that will make more sense when we look at this example about, once again, the SAT course. So although all that work that we've done so far on randomly assigning this particular scenario is really, this is the problem that those came from. So MHS offers an online SAT course with a classroom SAT course. That should say and. Offers, yeah. An online SAT course and a classroom SAT course. The counselors want to know which teaching method will yield higher SAT scores. 50 students have agreed to participate in an experiment comparing the two instructional methods. Counselors are certain that the student's GPA will affect their SAT score. So that is what we're trying to block. They're sure that if what they're thinking is, they're sure that if your GPA is high, your SAT score is high. If your GPA is low, your SAT score is probably low, which would make sense to me. So this, what we have highlighted in blue, is specifically what we are trying to block in this matched pairs design. So how would we block this? Well, we need to group these 50 students into pairs. So we're going to order the students by GPA from least to greatest. We're going to get our list of students. We're literally going to put them in the list from the lowest GPA to the highest GPA. Then we're going to pair the two students with the lowest GPA together. So we're going to pair the two students with the lowest GPA. Then we're going to assign one to the classroom, one to the online. We're going to flip a coin to assign one of those students to the online, one of them to the classroom. And then the indented bullet point describes how you would do that in detail so that you have an example of it. So let heads represent the classroom and tails represent online. Flip the coin. So decide what you're going to assign each side to, then flip your coin. The student with the lowest GPA in the pair will be assigned to the course that matches the side of the coin that is facing up. The student with the higher GPA will be assigned to the course that matches the side facing down. So we would do that for all 25 pairs. For all 50 kids, you're going to pair them by GPA. You want their GPAs to be similar. One will take the online, one will take the classroom, and then you'll compare their scores to each other to decide which one did better. So instead of having to write this, though, a bajillion times, you just say repeat this process for the next two lowest GPAs until all 50 students have been assigned a course. So by the time you're done, you'll have 25 pairs. By the time you're done, you'll have 25 pairs. So we're trying to block the effect that the GPA would have so that we can truly see which one of these methods produces a higher score. After the students have taken the SAT, we're going to compare their scores within each pair, combine the results from all 25 pairs, then make a conclusion. So when you describe your design method at the very end, they're usually looking for you to say something of the along the lines of compare, combine, conclude. Conclude is always last. So whether it's just regular hat method, two hat method, or a block design, usually when they're telling you, tell me how you would design this experiment, at the end they just want you to indicate, and it can be quick, that you know you'll compare within the block, then you'll combine all of those to make a conclusion. You're feeling kind of okay about this one? Okay, there's one more. It is matched pairs, which is still a block design. So we're still talking about blocks, and we're with this idea of it being a matched pair. But the word pair can be a little bit deceiving. So in this particular scenario, there is one experimental unit. One unit will get all of the treatments. So the difference between this one and the one that we're on is that every experimental unit does all of the treatments that are available. So sometimes each pair in a matched pair design consists of just one subject that gets all treatments one after the other. in that case, or in this case, each subject or experimental unit serves as its own control. The order of the treatments can influence the response. So we must randomize the order for each subject. So this example that we're going to look at has to do with a driving simulation. Did you guys have to do any driving simulations in driver's ed? Some of you did, some of you didn't. So when I was your guys' age, I was really book smart. Like, I could pass a test. I graduated with 4.0. I could memorize things. Could not drive to save my life. I don't know what the problem was. I get into driver's ed. I pass the written test with like 100%. Fail the driving test 3 times in a row. And I'm pretty sure that the teacher on the 3rd time, you had to get a 70. He gave me a 70. And I'm pretty sure that he only did that because he knew I was a good kid. I was just a dummy. I just needed more time to figure it out. So he passed me. Well, if you compare that to my sister, she's the opposite. I don't know that it's not that she's book smart, but she didn't care as much about her grades as I did. So her GPA was like a 3.0. But that girl could be a NASCAR driver. She passed her driving test on the first try. My dad let her start driving when she was 14. So if you put me in a simulation and see how many things I hit or how many mistakes I make and then give me a score, my score is going to be way lower than my sister's score, who's a better driver. Does that make sense? That's the premise for this problem, that each individual person has a different skill level. So in order to account for that, it's similar to the GPA situation. We want to account for how smart they are. To do that, we're going to compare each person to themselves. So what they're looking at is, does talking while driving distract the drivers? Now, they complicate this a little bit by saying you're going to talk on a hands-free cell phone. So researchers recruit 40 subjects for an experiment to investigate this. They have a driving simulator equipped with a hands-free phone for use in the study. Each subject will complete the 2 sessions in the simulator, one while talking and the other one while just driving. The order of the sessions for each subject will be determined at random. The route, the driving conditions, and the traffic flow will be the same in both sessions. So it has to be the same route. Like if you're driving through a neighborhood, it has to be the same neighborhood both times, because they don't want to do 2 different ones just in case one's easier. So what type of design would this be? This is a matched pairs design. Explain why the researcher chose this design instead of a completely randomized design. Before I fill in all these blanks, I just want to explain it in my own words. You have your 40 students, and what if a bunch of them are like me? You have a lot of really bad drivers and a handful of good drivers. Or what if you have a large range of ages? Like, what if you're allowing 16-year-olds and 18-year-olds to be in this experiment? I would bet that the 18-year-olds drive better than the 16-year-olds because they've been doing it for 2 years. Does that make sense? So if we just do 2-hat method and we say put half of them in the talking group and half of them in the driving group, we won't know if a bunch of the bad drivers got put in one group and that's why their scores were so much lower. So we have to choose a more complicated design so that we can block if there are just a bunch of bad drivers or a bunch of good drivers in our experiment. So the researchers chose this design, and we're trying to frame our answer as they asked it. So we're saying the researchers chose this design because some students might just be bad drivers or more distractible. The difference between the students, between their driving ability, will add variability to the response variable. That is the fancy way of saying the students' ability to drive, how good they are at driving, will affect their score on the simulation. So it will be harder to detect if there is a difference caused by the treatment. If we don't block their driving ability, we won't be able to tell if it was the talking that caused their score to be lower, because that's what they're looking for. They're looking for you to do the 2 simulations, and the one where you're talking, your score will be lower. In this matched pairs design, each student is compared with themselves. So the differences between students are accounted for. So they'll compare my talking score to my driving score to determine which one for me at my driving level was lower. They'll do that for every single student because that'll block the effect of driving ability, because you're just going to look at which score, which simulation had the lower score, and not necessarily at the scores themselves. So why is it important to randomly assign the order? So this one is, why do we want to choose this design? This question is, why do we have to randomly decide what one you do first? Because we can't have everybody do the talking first and then everybody do the driving second. So it is important to randomly assign the order because students followed the same route both times. It is possible that they could learn from the mistakes they made during the first session. So maybe on 2 of their turns, they didn't turn on their signal. So the next time they go in, they're like, okay, I got to remember to turn on my signal for every single turn. If all of the students used the hands-free phone first, so if all of the students were talking first in the simulation and performed worse, we would not know if the better score during the second session is due to the lack of phone, so is due to not talking, or from the fact that they remembered, okay, I got to turn on my signal every single time. I got to make sure that I come to a complete stop at a stop sign. We won't know, did they do better because they weren't talking, or did they do better because they made some mistakes in their first round and remembered to not do those in the second round? Randomly assigning the order of the treatments will reduce this variability. The variability is decreased because you'll have 20 students do hands-free first. So 20 students will talk first, and the other 20 students will just drive first. So randomizing, making it so that half of them do one treatment first and the other half do the other treatment first, helps make up for the fact that everybody's second score is probably going to be slightly better. Okay, last question. Explain how and why the researchers controlled the other variables. So this goes back to our principles of design, and it's just reminding us we have to have randomness. We have to randomly assign the order, but everything else we can and should control. The more we control, the better power we have to detect a real difference based off of the explanatory variable. So the researchers controlled the route, the driving conditions, and the traffic flow. So essentially, they tried to make the simulation the same, in the very least, the same difficulty. By keeping these variables the same, researchers are preventing them from adding variability to the response variable. So we're just saying, if we keep the route the same in both simulations, we don't have to worry about the route making their score better or worse. If we keep the driving conditions the same in both simulations, we don't have to worry about the driving conditions having any effect on the score. Is that making a little bit of sense? Okay, so we're going to go on to 919. It's our last problem for the day, and we're going to look at all of them compared to each other.